to Linda.
Yes, thanks a lot, Katja. It's my pleasure to warmly welcome Pascal Friedrich for our colloquium today. He holds a professorship in artificial intelligence for material science. And yes, he has an international career with stations in Harvard and Toronto. He's now at KIT, first as an assistant professor since 2025 as a full professor with two affiliations, the Institute of Nanotechnology and the Department of Informatics. His research has been prominently awarded by prizes. And he will talk today about three different topics about the role of AI in material science and chemistry, what is the potential there, and how does it also bring it support for accelerating materials and also the discovery of molecules. You will also present your research, which is dedicated to self-driving labs and automated data analysis, and how also automated decision making is pursued in experiments. And also, you will speak about how you use large language models to predict also research topics for material sciences. And since we are also focusing on the digital transformation of research in this interdisciplinary consortium, all three topics are of high interest for us. And I think especially the last topic is also very much interested, not only for informatics and material sciences, but also for social sciences. You are not only you are a professor for artificial intelligence for material sciences, but you are also very much interested in the societal impacts of artificial intelligence. At least you lie here focused on your teaching, and it's important for you that you teach also your students what the societal impact of artificial intelligence is. And we had the pleasure to collaborate here. And so I'm also very much looking forward now for your topic talk on AI for material science, and I'm looking forward to the interdisciplinary discussion after your talk. So, Pascal, the floor is yours.
Thank you very much, Linda, for the very nice introduction. And thanks, Katja and Linda, for inviting me to this seminar series here. It's my pleasure to be here today and talk about a bit of our research in AI for material science. And as Linda said, we will focus on mainly two aspects. One, how can we use AI to autonomously decide how to run experiments, how to optimize materials in an efficient way. And then I will go to a more broader question of how novel ideas can be generated. But before I start with this, I would like to motivate why is materials research even so important and of high societal relevance. And the main argument here is that materials are one of the key drivers for innovation. And this is true for more or less for all kind of technology areas, spanning from renewable energy, photovoltaics, batteries. Progress in all of these areas is driven by discovering, optimizing new materials and bringing them into new applications. This also is true for electronics, chips, semiconductors, or entire digital world is driven by progress here. But it also doesn't stop in life sciences, medicine, developing of new antibiotics, vaccines. This is all driven by molecular discovery, molecular optimization, and then all the materials engineering around this in order to make this useful. And of course, like this doesn't stop here. There's many other areas, mobility, transport, aerospace, a lot of other relevant application areas where new materials are required in order to make progress on the technology side. But at the same time, just exponential growth in all of these areas is not sustainable. So we also need to think about how can we make materials that are long-term sustainable, that are driving technologies that can be recycled, that can be maintained over long term. And this is why we need at the same time to not only have better materials for specific applications, but also fulfill certain sustainability requirements. And this, of course, also requires us, and certain things like climate change also is very urgent to be addressed by, for example, developing new materials for clean energy technology. So we need urgently battery materials. We need solar cell materials that are more efficient, more durable. We need new magnets, for example, for electric motors. So we need not only good high performance materials, but also materials that fulfill sustainability requirements at the same time. And this is a huge challenge. And material science is now at basically in a position where we have, on the one hand side, an infinite search space. We have infinite amount of potential molecules and materials that we could use for specific applications. It's really hard to find the material, the molecule that has all the properties that we need. But at the same time, this, of course, is also an opportunity. There's very likely new materials out there that have not been thought of yet, that have not been discovered yet, that have not been made yet, that have exactly the property profiles that we need to have at the same time high performance materials and at the same time also sustainable and recyclable materials. And this challenge needs to be addressed in some areas quite urgently. And this is why we need to think about how to search in the search space more efficiently. And this is some of the topics that we cover in our research group, is how we can use AI and machine learning methods. How can we also discover or develop new AI and machine learning methods that can solve challenges like this? Specifically, how can we use AI and machine learning to complement experimental science, theoretical science, also simulations that already exist in the best way to accelerate the progress there, to find more useful materials faster. So we work on the one hand side on method development and computer science, develop new AI and machine learning tools that can help researchers in material science and in chemistry to find new materials faster. But then we also heavily focus on a couple of applications because we don't have our own labs. We collaborate a lot in this area to bring our new methods into application, to bring them into the lab, to see how we can train them on specific classes of materials, for example, photovoltaics. I will have examples of that later, to really translate that research into something that we can, in the end, hopefully hold in our hands and use, for example, in form of a solar cell on a rooftop. And today I would like to focus on two aspects of our research. And this is the decision-making algorithms that are driving the self-driving labs. So we have a lab that kind of can do experiments in a more or less automated way. And now we need a brain that kind of learns from the experiments that are being performed and then decides what is the most informative next experiment to do. This is what I will focus on in the first part of the talk. And then I will take a step back and look at the bigger picture. If we can define something like a self-driving lab with a fixed workflow, can we maybe even come up with new ideas in an autonomous way that use that self-driving lab or use the tools that we have in more interesting new ways? So the question, how can we create new scientific ideas using AI in an autonomous way? So let's start with the first part. And the idea of what we call self-driving labs or materials acceleration platforms, there's many different words for this idea, is we want to close the loop. We want to close the loop between an interesting experiment. This can be in material science, in chemistry, in biology, in life sciences, no matter where. So we have an interesting lab experiment that in principle has many different options. It has a lot of parameters. We can search many different types of materials, many compositions, many processing parameters. We have a large design space. And that design space is so large that we cannot just by brute force try all different combinations, try all combinations of elements, try all different processing conditions, try all different combinations of how this can be done. So we need some sort of clever decision-making algorithm to find the optimal material, the optimal synthesis route, the optimal processing that makes the material have the properties it needs. And then we couple this with, to some extent, automation in order to close the loop. We don't want someone to stand in a lab and do all the steps manually. We rather want to have a certain degree of automation. This doesn't need to be fully automated, but partially automated, so all the bottlenecks that are in the experimental workflow are more or less done by robots. And then we couple this with AI. So we're moving away from this paradigm of AI where we first generate a very, very large data set and then we train a very large model on this data set and then make a prediction. This is not what we do here. What we do here is we close the loop. So every data point is expensive because the lab experiment really needs to run and it takes a couple of hours or even days. So every data point is valuable, and we want to learn from every data point that is coming in to update our model, to inform our model, and to let our model make optimal decisions in that given moment in time. So we're closing the loop using experiments, automation, and AI. And then with every data point that is being measured in the lab in a more or less automated way, we inform the machine learning model to do informative next decisions. And there's a couple of algorithms that can do such a thing. This is not large-scale machine learning. We're not training typically very large models here. Typical algorithms that are being used here are Bayesian optimization. That's a paradigm where we train a model iteratively to optimize a certain set of parameters, which is basically what we have here in the lab. But nowadays also there's like agentic workflows that complement Bayesian optimization and all kind of new ideas how we can make this closed loop more efficient. But I would like to fill this with some life. And we had the pleasure in the last couple of years to collaborate with many experimental groups to kind of try out how can this be realized in a real world lab. And this spans many different applications. For example, here at KIT, we collaborated with the engineering department on optimizing ceramic materials for additive manufacturing. We worked with soft materials, also here at KIT with Pavel Levkin on, for example, developing responsive polymers that have a certain UV light response, but also with other national and international collaborators. We worked on different classes of materials, filtration membranes for water filtration of heavy ions, catalysts that can more efficiently split water into hydrogen and oxygen. This was a collaboration with Forschungszentrum Jülich. We worked on electrochromic materials that are switchable by applying a voltage. They switch their color. And as I already mentioned before, one of our main focus areas is photovoltaics materials. Here we heavily collaborate with the Forschungszentrum Jülich and the Helmholtz Center in Erlangen and Nuremberg with the group of Christoph Brabek. And Christoph Brabek was building in the last couple of years, or maybe even like a decade or so, a super impressive autonomous lab. His specialty for many years was the automation of device manufacturing and device testing. So he automated the entire thin film processing that's required to make a organic or perovskite solar cell. And in the last couple of years, he even added the chemical synthesis of the starting molecules, the starting materials that go into the solar cells to this workflow. So we have a full workflow experimentally that covers all the steps from synthesis of individual molecules, characterization of these molecules, then making the solar cells out of thin films. Solar cells are typically a stack of many thin films, and then characterizing these solar cells, testing their device performance, all the way to even like aging testing and so on. So experimentally, this whole workflow is more or less automated. And this, of course, gives us a large amount of opportunities to now think about how can we make in a AI accelerated way decisions about what molecule to synthesize next in order to have a promising candidate for a very promising solar cell efficiency. This is what we tried in the last couple of years. We first had to define our design space. So we said, okay, we can make molecules in a combinatorical way. So these molecules consist of building blocks, like Lego building blocks. We can make ABA type molecules. So we have a set of potential A building blocks and a set of potential B building blocks. If we now like buy a library of 1,000 A and 1,000 B fragments, this already means we can make 1 million potential molecules. If we even allow AB and then a different A, so ABA prime, this would already be 1 billion molecules. So we can span very large design spaces quite quickly. What we did here was this design space of 1 million molecules. And those molecules will act as a whole transport layer in perovskite solar cells. So a perovskite solar cell has an active layer where the sunlight is being absorbed. It's being split into electrons and holes, and then these electrons and holes have to be transported out of the solar cell. So we need not only the active solar cell material, but we also need additional materials. And here in this case, we focus on this whole transport layer to get all the holes out of the solar cell. And this design space is very large. We cannot just, even though this is fully automated, we cannot simply synthesize all these 1 million molecules and make the solar cells and test them. So we need digital methods, AI methods that can, from a small subset of these molecules, learn how is the relationship between the molecular structure and the performance in a device. And then using this learned relationship, we can make clever decisions of what is the most promising molecule to use next. So what are molecular motifs, molecular combinations that are very likely to perform very well? Or, and this is the part of patient optimization that makes it very interesting, we can also ask the model what molecule is very uncertain given the data that we measured so far. So if we start, and this is what we did here, start with an initial database of roughly 100 molecules, we can ask the model A, what is the most promising molecule? And this, of course, is a good decision to try next. But we can also ask it, which of these 1 million molecules does the model not, like, where is the model not able to say anything useful about which molecules, or which molecules not covered well by the initial database? So what are highly uncertain predictions? Because those are kind of important to explore the chemical space very efficiently. So we need to explore like kind of balance between finding very promising molecules and finding molecules that are really new and novel and look very different from all the molecules that have been discovered yet. And then we can close the loop. We can make multiple iterations. In this case, we only did 2 iterations because it was so costly. Each iteration was roughly 10 or 20 molecules. So we let the algorithm train based on the initial data set. We enriched this with some DFT calculations, so there were some additional simulations being performed to inform the model a bit more. And then the model was deciding what molecules to do in the next iteration and how to efficiently optimize in this space. And then over these iterations, we found molecules that are much higher performing than the molecules in the initial data set. And then further optimization of all the other parameters in the solar cell, like layer thicknesses, combinations of materials, and so on, led to a 26% solar cell efficiency, which was for a very short time. It was a world record in perovskites of solar cells. This is a very competitive field, so the world record was not very long standing, but still we could discover a new material, a new molecule that could push the efficiency of the perovskite solar cells by having an optimal whole transport material to a very high efficiency. And we didn't only find one of these new whole transport molecules that really leads to high device performance, but we found multiple ones, and those could now be also potentially matched with other active materials, because the solar cell in the end does not only depend on this one molecule or one material, but also on a combination of all different other materials. So this is kind of demonstrating that decision making based on AI and also based on all the data we can get from simulations and experiments can be complemented to close the loop here in order to make decisions in a very data efficient way, in a very overall experimental efficient way. So with the fewest amount of experiments, we can hopefully find the best performing materials in a very complex scenario. And this is also something we're doing in Helmholtz as a whole, not only in this one photovoltaics example. So I would like to quickly introduce the Helmholtz acceleration lines here, which is a new initiative in Helmholtz that tries to develop a decentralized platform of such self-driving labs in many different areas. So the idea is to have not only one isolated self-driving lab, but we have multiple different ones that can, for example, synthesize different classes of materials, from biomaterials on the left-hand side to inorganic materials here on the right-hand side, and then also go into different application areas. So we can, in principle, machine learning methods that can decide, okay, I want to synthesize new material here in this one lab, and then I want to ship this material to another lab that can make maybe a different interesting application out of that, or use that material in an interesting application. So we can kind of have decentralized workflows across different labs in Helmholtz, maybe also beyond Helmholtz, to take this to the next level and to really have workflows across different labs driven by AI in a very data efficient way in order to make material science more systematic, to reuse all the data that is being generated in different sites, put this all into a central model or into multiple central models that learn from all the decentralized data to make interesting decisions, and also to test interesting experiments, or maybe even interesting workflows that span different sites in Helmholtz to accelerate the discovery of new materials for different application areas. And this brings me to the second part. If we have such a network of self-driving labs that all have different capabilities, that all have different materials classes that can be synthesized, different applications that can be covered and explored. This opens a huge design space. We open the design space from just automating given parameters, like in the solar cell material, we want to given, like the solar cell, as I said, consists of these A and B block molecules. So we had a very confined design space of find the best A and find the best B block molecule, and maybe also optimize the layer thickness. This is a very local optimization problem. Here now we can open this up to a much more global type of perspective on material science. So basically open it up to questions of how do we find better materials for a given application. And this then also lets the algorithm potentially optimize what material classes to choose, how to process them in what different processing techniques, how to put them into devices in interesting ways. So this opens up for much more creative ideas that can be potentially fueled or inspired by AI suggestions. And this is what I would like to cover here in the next couple of minutes. And if we want to discuss such an open problem, we need to kind of look at this in a more systematic way. So if we think about scientific progress, we can look at this diagram here where we have in the top left corner the known knowns, so all the scientific knowledge that we already acquired over the centuries and millennia. We have in the bottom left the unknown knowns, kind of our intuition, things that we're unaware of that we know, and this is a bit hard to systematically put into words. But then on the right-hand side, we have all the unknowns. We have known unknowns. Those are things that we're aware of that we don't know yet. And one example is, for example, we know that something like superconductivity exists. We know it can extend to quite high temperatures, but we don't know yet a material that can be superconductive at room temperature. So we know we discovered a phenomenon, but we did not discover yet the material, or we don't know yet if there's even a material that is superconducting at room temperature. But this can be very systematically researched by trying different materials classes, combining different knowledge that we already have to push that limit of high temperature superconductivity. And in the bottom right corner here, we have the unknowns, and those kind of are things we're unaware that we don't even know them yet. And this is something like discovering a phenomenon like superconductivity. So the first time it was discovered, before that, there was no systematic approach of finding this because no one even knew that such a thing could exist. You can argue that it was kind of in the unknown knowns because the underlying equations, Schrödinger equation and so on, was already known and is a kind of direct result of the Schrödinger equation. So the formalism behind it is known, but it was not clear that we can derive something like superconductivity from the Schrödinger equation. So this is kind of an unknown area, and this is what I would not try to tackle here. But what is more interesting to tackle is the known unknowns. So let's focus on this area and kind of make here a linear diagram from the known knowns over the known unknowns all the way to the unknown unknowns. And I would argue now that we have like a different level of creativity of ideas that we need in order to go from left to right. If we take only the known knowns, we can maybe take existing concepts that are already well explored and discovered and improve on one of them in a more or less incremental way. And this is what I would say, this is what self-driving labs mostly right now are focusing on in order to develop some proof of principle studies. So we have something like photovoltaics is quite well understood, and we can improve on it by finding better materials, finding better combinations of processing conditions and architectures to make it better. And then we can also think about bringing new concepts together. For example, taking a materials class that is being known and not explored it for photovoltaics, but discovered that this could be useful for photovoltaics. So we can kind of combine concepts that exist. And this is already a more unconventional idea. And then we can introduce entire new concepts, but this is kind of already leaking into that unknown area, which means we kind of need true discoveries for that, experimental discoveries. So this can only be done by a combination of AI and experiments. And the same thing for transformational ideas of replacing entire concepts. This is something that cannot just be done by looking at data that already exists today. You typically need a combination of experiment and AI. So this is what agents, LLMs can maybe potentially do already today. This is where experiments are required, and typically also to some extent human intuition and expectation or observations of seeing that there's something really truly new in the data, but this is something where potentially AI can help with bringing concepts together that are not combined yet, but that have a big promise of being combined in a interesting new way. And this is what we focused on here in this study. This is done by Thomas Marwitz, who started as a bachelor student in my group and who was driving this research for the last couple of years. It was very impressive to see how a bachelor student can develop such a topic. He will now start very soon as a master's student, but he was doing this all during his degree program in computer science. And he, in order to combine concepts, first needed to make basically a list of what are existing concepts in scientific literature. And because scientific literature is huge, we focused on material science first. So we looked at all the data, all the papers that are published in OpenAlex that are in the core material science area. This is 200,000 papers roughly. And from that, we used large language models to extract the scientific concepts. And from these 200,000 papers, we got something like 100,000 concepts. Thomas is now extending this to the more broader material science, life science, chemistry area, where the paper data set is much larger. So we go from 200,000 to 11 million. The number of concepts, to some extent surprisingly, also more or less linearly scales up. So we, instead of 100,000 concepts, we have now more than 1 million concepts that occur more than 50 times. So we see already here we're quite creative in science to introduce new scientific concepts. And now we want to combine those. I'll skip this. So combining these needs to somehow, we need to find a representation. And this is what we do here. We generated large language model embeddings of these concepts. And now these embeddings you can think about as kind of vectors on a map, so coordinates on a map. So you can make basically here a map of material science, all the different concepts that are being mentioned in material science, and you can cluster or map them out by similarity. So for example, all the electronic materials will be here in one corner of this map. All optoelectronic properties are in another corner. Processing techniques are somewhere else. Vacuum processing is neighboring solid processing. Steels are somewhere else. So there's different materials classes in this map. So you can see this map kind of shows an island or many islands of different concepts in material science. And now we want to combine them, and not only combine them by how close they are in this map, but combine them based on an idea that was published by a former colleague of mine, Mario Kren, who was also a postdoc in Toronto when I was there. And here this idea of now looking at such a concept data set and generating a concept graph out of this. So every node in the graph is one concept, and every link that combines two nodes is a paper that mentions these two concepts together in the abstract. So if we have a paper that combines concept 1 and concept 2 in the abstract, and this was published in 2009, then in this graph we generate a link between concept 1 and concept 2, and this link carries the information. This was published in 2009. And then we can train a model that predicts the likelihood of concept 3 and concept 2, for example, being mentioned together in the paper in the next couple of years. So we can train our machine learning models that learn from this concept graph and how it evolves over time to predict kind of missing connections that are kind of already by similarities and connectivities of different concepts being encoded there, but they have not been really published yet as a new paper. So we can now predict for all non-existing links, for example, the concept 2, concept 4 link, what is the likelihood that these concepts will be co-occurring in the same paper in the next couple of years. And this idea works surprisingly well. So we can take then a graph on the state of 2016 and then predict for the time span of 2017 to 19, what are the concepts that should co-occur. And then we can test this because we know what has been published in 2017 to 19. So we can test what is the true positive rate of our model being correct in predicting a link connection that was then actually published in this time span versus what is the false positive rate where the model predicted these two concepts should be mentioned together, but there was actually no paper published that did combine those two concepts. And the challenge here is that there's basically an infinite amount of possible connections. So we want to have a very low false positive rate. Otherwise, the model would predict a super large amount of papers being published. So we want to be very far left on the graph. And the more further left we go, these lines indicate that then this means also the true positive rate will go down. but we can kind of find a sweet spot here where, for example, the false positive rate is just, I don't know, 5, 6, 7%, while the true positive rate is still at 70% or so. So from every prediction that the model makes, it's 70% likely that there will actually be a paper being published in the next couple of years. And with this model, we were kind of happy. I mean, you see here in this chart, we tried different ways of doing the machine learning model, of how to represent the data and so on. The best model was in the end this yellow model, which was actually a combination of multiple models. And then we wanted to test this because this was now kind of just a dry test of previous papers that have been published. Now we wanted to train a model on actual data right now to predict and recommend to researchers what they should be looking into. So we took the individual papers of researchers that we found in Google Scholar, and then we made individual concepts based on these researchers' profiles. And then we made individual suggestions for these researchers of what combinations they should look into, or that according to the model are promising to look into in the next couple of years, that are, according to the model, have a high likelihood of being mentioned together in the next couple of years. We tried this with multiple researchers. So we gave them, each of them, I think it was 10 interviews. We gave 10 researchers their individualized recommendations, roughly 20 of them each. And then we asked them to categorize this. And the categories we asked them for was A, this is already known, or this is a trivial combination that should have been already mentioned, but the model somehow missed it. So this should have been, there's nothing new in this. B, and this is an interesting category, the researchers couldn't even make sense of why the model suggests these two concepts together. This could be the case that the researchers didn't even know one of these concepts, because specifically here, one of the concepts was their own concept, but the other concept could have been a concept that they never published on and that they might not be familiar with, because not every researcher knows all the, I don't know, hundreds of thousands of potential concepts in material science. This is such a diverse field that no one knows all the different techniques and classes of materials and so on. But this could also be the case that there's just no spark of inspiration by showing these two concepts together. And then C is the class we were looking for, and this is where the researcher said immediately, oh, this could be a good, interesting combination. I would need to look into this a bit further, think about this a bit more. But what we found is this category C has a rate of roughly 20%. So 20% of the recommendations by our model were deemed as interesting and worth of looking a bit further into. We had one very lucky guess where a researcher said, oh yes, this is something I'm writing a proposal about right now. And he could immediately kind of put out his proposal, even show us a graph of things that he wants to look into in this area. And other researchers also said this is at least an interesting thing to think about and maybe pursue further. And this is where we're at right now. So here's the people we interviewed, a couple of examples of the recommendations that we're giving. I mean, for the non-material scientists, this might not make too much sense, but for example, this conventional ceramic materials plus graphene oxide was the recommendation that we gave to Ben Breitung here at KIT. And he said that this is something he was already thinking about. There's no paper in this area yet, but he has a good idea of how to combine this and how this can be useful to improve the properties of these ceramic materials. So this is working quite nicely to just like inspire new interesting ideas in research. Of course, this is only a 20% success rate, but in the end, if I don't know, get in the morning from my AI assistant 5 new ideas, and one of them is good enough to write a proposal about, this is already a quite high success rate. And now we are looking, of course, to pursue this further and this is now more or less a human in the loop thing, to also implement these ideas and turn them from an idea into a concrete work plan. And then in the future, potentially with automated labs, also then more or less in a semi-automated way, also implement these ideas in self-driving labs in an automated way. So there's many of different areas that come together here. So the AI research to make these ideas possible, agentic AI to also help humans to implement them faster, and then all the automated and self-driving labs to then make ideas and make work plans reality. So I think we're looking ahead to a very exciting future in materials research and also beyond. And with this, I would like to close my talk. I showed today how AI can help us to accelerate automation and optimization in self-driving labs, and how we can even move more towards autonomous or human-in-the-loop science to expand what we can do today. With this, I'm at the end of my presentation. I thank you very much for your attention. I'm very happy to answer any questions that you might have.